So I'd like to start with this slide, which summarizes our understanding of all the physical factors that limit the quality of the biological cryo-EM data. In terms of a B factor, which is just a number that we assign to assess the relative quality of images. So we have a few main problems. Radiation damage, which causes the quality of our data to deteriorate steadily throughout the exposure. We have a few minor contributors which we don't worry about much anymore, such as charge fluctuations, Brownian motion of the water molecules surrounding the sample, and charge buildup, provided that we use conductive specimen supports, which this talk is going to be all about those. And finally, we have motion of the specimen, which quite unfortunately happens to be worst in the beginning of the exposure, where the specimen is least radiation damaged and causes this really unacceptable data quality loss. So, in a sense, this talk has two parts, and they're about these two big problems, motion of the specimen and the radiation damage, which happen to be quite intertwined. All right, so in first part, I'm going to talk about how did we learn to do cryo-EM without any specimen movement. And in the second part, I will talk about how did we learn to use this movement-free cryo-EM data to actually mitigate the effects of radiation damage to our final reconstructions. All right, so if you're going to get one takeaway message from my talk, it'll be quite simple. Switch to using all gold grids in favor of using any grids with carbon support foils. And this is because the supporting foil that will actually surround your freestanding specimen in vitreous ice tends to move during irradiation, and the difference between carbon and gold is huge. With both with and without specimen, and both in the in-plane direction of the support, but also transversely. So in this talk, everything I'm going to talk about is going to be about grids where both the grid bars and the grid foils are made of the same conductive material, gold. All right, so why do we worry about specimen movement if we have all these programs that, in a sense, deal with it, starting from the very early days of the single particle cryo-EM. And why do we have so many programs that deal with this? I guess the part of the reason is that none of these can track the motion of the particles during the exposure perfectly, because the images that we acquire are inherently very noisy due to the limitations imposed by radiation damage. So it is hard to track how is the specimen moving as we're trying to image it. And these plots just show the relative quality of the data during cryo-EM data during exposure, evolving with fluence and evolving with time from 2014, around the first direct electron detectors, when this kind of measurements became possible, and to kind of this year. And of course, throughout this time, all the algorithms improved, and we learned a lot about specimen supports and how to make better specimens. But one thing remained invariable: the quality of the data at the onset of the irradiation is always lower than this linear trend that we accept from X-ray crystallography, where the quality of the data decays purely due to radiation damage. So if we were able to take account of all the specimen movement computationally in our cryo-EM data, all of these plots should have been straight lines, which they're clearly not. And these shaded regions on each of these plots demonstrate roughly how much in terms of data quality we've lost in total due to not being able to sort out our specimen motion. So this is still something that we need to address beyond just trying to account for it computationally. So to be able to address it, I guess we need to briefly talk about what types of specimen motion we see in cryo-EM. I'm just going to go through this basic stuff very quickly so we're all on the same page. So we have a stage drift, which is a time-dependent, fluence-independent phenomenon, which with the more stable microscope stages and fast electron detectors is now very easy to account for. So this is not really a problem for us. But beyond that, we have movement of the actual supporting structure, which I already talked about, where the foil that supports the specimen is bending as you're irradiating it. And there is this big difference between the carbon support foil and the gold support foil, which will be very visible in this video, where in the bottom insets you will see how the edge of this hole will move during the exposure. And as you can see, for the edge of the carbon hole, it basically came all the way over here, and the gold edge hardly moved. So again, this was mostly solved by the introduction of the all gold specimen supports. But even after that, if we look at the vitrified within one hole like this, we would see that the particles within the ice are moving relative to the hole, which is not moving anymore. And we attribute this collective, somewhat correlated motion of the particles within the ice to a deformation of the slab of ice as a whole. And further, the water molecules within the ice are moving when they're being irradiated with high energy electrons. This results in a pseudo-diffusive motion that looks very similar to a thermal diffusion. And these water molecules would kick around the more massive protein particles and move them by a little bit. And of course, we're not at zero temperature, so we also have the atomic movements, but they're so small that for the resolutions that we can achieve, this doesn't really matter. And there's been a lot of development on different types of cryo-EM specimen support, starting from these carbon foils with graphene, then all gold grids and gold grids coated with graphene. But we've never been able, until recently, to make the amount of motion that we measure for the particles supported by these grids, make it as small as the diffusion limit set by this Brownian motion. So there's clearly something that we were still not being able to control. So in my PhD, we started to investigate these patterns of particles moving within the ice supported on gold foils. And we looked at the movement of these particles both in the plane of the foil, but also perpendicular to the plane of the foil by taking untilted and tilted movies. And we looked at the displacement as a function of fluence for different hole sizes. And there are some clear patterns. There are large displacements at the very onset of irradiation, both in plane and perpendicular. The larger the hole, the larger the total displacement and the initial displacement. It's always bigger for the tilted image rather than for the untilted, meaning most of this displacement is out of plane relative to the foil. But quite interestingly, you go to a small enough hole and these trends break down. The amount of motion becomes insensitive to the size of the hole. So for a 0.2 or 0.3 micron hole, it's exactly the same. And the amount of in-plane motion becomes the same as the amount of transverse motion, meaning that this motion is isotropic. So whatever it is, it's kind of lost awareness of where the plane of the foil was. Which is quite interesting because an example of isotropic motion, of course, is the Brownian motion. And if you make the calculation, this amount of movement that we measured in these small holes is exactly the amount expected from the Brownian motion of the water molecules within the ice, kicking around these much more massive gold nanoparticles within the ice. So we thought this is very interesting. It turns out that if we make the hole in the supporting foil small enough, we can remove all the non-Brownian component of the movement, which is the correlated movement of the ice as a whole, which we, from these measurements and from the trajectories of the particles, seem to be some type of a buckling deformation. So then we started thinking, what could be the reason that the ice would buckle? A simple way to think about it is to consider a uniform disk of some material under compression. Then it would be very easy to calculate what is the critical compression N in the plane of the disk required to buckle this disk. And it turns out it depends on very few parameters. It depends on the Young modulus of the material, assuming the support is much, much stiffer than the ice. Depends on the thickness cubed of the ice. Depends on the radius of the unsupported ice and on the Poisson ratio, which is another elastic property of the material, just a constant. And then we thought, what could be the origin, if this buckling actually happens, what would be the origin of this critical compression to cause it? One idea was that this could be caused by the specific volume change in the ice during plunge freezing, because the specific volume of the water at the starting temperature, let's say room temperature 4C, is different than the specific volume of amorphous ice at 80 Kelvin. And then the force caused by this is proportional to the bulk modulus of the ice and this specific volume change and the thickness. And then if we combine these two equations, we actually obtain an equation for the critical aspect ratio of the thickness to the radius of the ice in the hole, above which this unsupported ice is actually stable and it will not buckle during freezing. And it turns out it depends only on two parameters of the water itself, which is the change in specific volume and the Poisson ratio, which is basically two constants. So this is, in the end, just a number. So there should be a very simple threshold above which, if the size is thick enough or the hole is small enough, it's stable. And conversely, if the ice is too thin or the hole is too big, it's not stable and it will buckle during freezing. So what we envision is happening with these cryo-EM samples is the following. If we look at the first plot, here I'm showing the density of water as a function of temperature. And before we start vitrifying our samples, we have just this liquid film stabilized on our foil. We are somewhere here at 4C and the density of water is around 1. Then we plunge very quickly. In less than 0.1 millisecond, we will end up somewhere here at below 100 Kelvin. In this very short amount of time, we will cross a few interesting points. Firstly, we will cross the homogeneous nucleation point of the water, after which basically the freezing begins. And after that, this is essentially now a piece of solid material which can build up stress. And as the density of the water changes upon further cooling, more and more stress is built up in this thin disk of ice. And when the stress is large enough, the disk will buckle. And then it will continue cooling even further. The density will continue changing, which potentially will deform it even further. But then this remains in our storage dewar or in our microscope for a very long period of time at around 80 Kelvin and is basically indefinitely stable, right? Because the diffusivity of the water molecules at these temperatures around 80 Kelvin is vanishingly small. So this buckled disk of frozen vitreous ice in itself is stable. The problem is when we start irradiating it with high energy electrons, as soon as we start acquiring our movies. During the electron irradiation, the mobility or the diffusivity of the water molecules goes from here to here, increasing by more than 40 orders of magnitude. Or if that is because some energy is deposited by the electrons into the specimen. If you like to think about diffusivity in terms of temperature, that would be equivalent to having the film at a local instantaneous temperature of around 150 Kelvin, and which on this plot is somewhere here in the no man's land, where quite little is known about the properties of water. But whatever the properties of water are in this region, they are not the same as at 80 Kelvin, which means that the film that was in equilibrium when it was frozen at 80 Kelvin, as soon as it's irradiated, is not anymore, and it continues deforming. And this deformation is both enabled by and carried out by the interaction of the electron beam with the water molecules. So this is our rough understanding of what happens and why cryo-EM specimens move. And of course, how we combat it, we just never allow the specimen to buckle during the freezing. Then there will be no uncompensated forces during this change that occurs when we start irradiating the specimen in the TEM. So we have this equation for the critical aspect ratio. If we plug in all the numbers, depending on some assumptions we make, the ratio of the optimal diameter to thickness is something between 15:1 and 11:1, meaning if we have our standard cryo-EM specimen support we're used to, something like a 2-micron hole spanned by 300 angstrom thick ice, the ratio is almost 100:1. This is not stable. However, if we had roughly the same size hole spanned by a very thick piece of ice, more than 1,000 angstrom, we could arrange for the aspect ratio to be 10:1, which according to this theory would be stable. So this specimen would not buckle during freezing, and then during irradiation it would be stable. However, for the single particle cryo-EM, we don't really want to make the specimens that thick. The ideal thickness is still a couple hundred angstroms over here. So the way to achieve that and make those specimens stable would be to make the hole very small. As we showed, something like 0.2, 0.3 microns turns out to be appropriate for the needs of the single particle cryo-EM. So of course there is one problem. This is not commercially available. You can buy grids with holes starting from around 0.8 microns and up. So even to make these preliminary experiments, we had to figure out a new way of making these supports with 5 times smaller holes than what was available. This was all described in this paper, which you can have a look at. And we've shown that the motion in this specimen supports with these small holes, which we call them the hexafoil, is exactly as predicted by the pseudo-diffusion limit. So there is no collective deformation of the ice. And the total amount of displacement within a typical cryo-EM exposure is less than 1 angstrom. So this would now not limit our data quality. And this is what these grids look like that we learned to make and made ourselves. So again, it's a 3 millimeter grid, just like any grid you've seen. The grid bars are made of gold. If you zoom in, one grid square is not actually a square, it's a hexagon. But that's just a design choice. This is not really related to the properties of the specimen support. But we figured since we're going to make the whole thing from scratch, why not pack as many areas as possible? So the grid squares are now hexagons, and the holes are also arranged in a hexagonal array rather than in the previously used square pattern, which you've seen in all the commercial grids. In this way, you fit a few, like 1,000 hexagons on the grid, and within each hexagon you fit around 7,000 of these small holes. And one micrograph of one 200 nanometer hole would look like this. So if your protein is at a high concentration, you would still have quite a lot of particles. We're hoping to make these grids commercially available via Quantifoil very soon, so that everybody can use them and collect motion-free cryo-EM data. They're also great for the modern data collection strategies because, as you see, you have so many holes per unit area that if you want to collect data with image shift instead of stage shift, almost 1,000 holes are within reach and you don't even have to move the stage. So this combines nicely with the high throughput data collection. So with the anticipation that these grids will be available soon, I just wanted to give a few practical tips for those of you who will get them soon. First of all, how to prepare the specimen on the Hexafoil grid. Well, the quick answer is just as normal. You just freeze the specimen on the grid that's been plasma cleaned before that to make it as hydrophilic as possible. And one tip I would give is that because the hole is smaller, it's hard to overblot these grids, so I would say blot longer and stronger than for the large hole grids that you're all used to. And then for data collection, luckily with cryo-EM things are super flexible, so you can just set up your own presets and go. For the EPU users, we've worked with TFS to support this type of grids now, and all the versions higher than 2.14 recognize the hexagons without any problem, are able to find the small holes without problem, and recognize that the holes are in a hexagonal rather than in a square arrangement. And the cool thing is, if you want to acquire a 20,000 micrograph session, you only need to pick like 3 or 4 grid squares and press run and leave, because you have so many areas per hexagon. However, because you will be trying to target these small holes for each of the acquisitions, your alignments need to be pretty good, otherwise you will end up taking images of the gold mostly, and especially the AFIS calibration is going to be crucial to make your images go nicely into the centers of the holes. And it's nice if you have fringe-free illumination on your microscope so that you can condense the beam to a size similar to the size of the hole without getting the fringe from the edge of the beam into your image. But it's not essential because you could also just expand the beam and give up on all the neighboring holes of each targeted hole. All right, and after you've collected your movement-free data with the Hexafoil grid, there are some changes to how you would have to process it. First of all, virtually all of your images will have a little bit of gold in the corner. That's actually nice, because you can use the diffraction of the gold to very accurately calibrate your pixel size directly from the data. And we're hoping to release a program that does it automatically soon, and in the future it's probably going to be just incorporated into your standard processing pipelines. Because there is no specimen motion in these grids, there is no need to do anything fancy about motion correction. You're just required to do a whole frame alignment for the stage drift, and that's it. No patches or no tracking is required because there is no motion. You could still try to do it just to check. And finally, the ice supported within these small holes tends to be quite flat within the hole. So unless you're going for some really high resolution beyond 2 angstrom, no significant defocus variation or variation in height between the particles within each hole is expected. So there is no need to do things like per particle defocus variation, just simply because there isn't, because all the particles are in this thin, flat slab of ice, which actually makes things easier. This is how the motion-free data is better than data which would require motion correction. So here we've collected the same specimen on 2 supports, the Hexafoil and a carbon foil. In one case, we have applied no per particle motion correction and obtained the sub-2 reconstruction and calculated the Rosenthal B factor. In the other case, we've applied all the possible motion corrections and obtained the red transitioning to brown Rosenthal plot. And interestingly, the B factors are different, especially in the high resolution range, meaning that these effects of uncorrected sample motion really only kick in after you pass some resolution around 4 angstrom. In the low resolution range, this doesn't really matter. But the high resolution you go to, the more advantage you have from having this higher quality movement-free data, which enables you to also get a reconstruction of a certain resolution with lesser amount of particles. So just to summarize, if you want to collect movement-free data, you have to use a all-gold specimen support with the optimal aspect ratio, where the diameter of the hole is safely 10 times the thickness of your eyes, and then the data will be movement-free. And this is just demonstrated by this B factor as a function of fluence plots, which we have now done for a few different samples collected in this type of grids. And now, satisfyingly, all of these are straight lines, as expected, purely from radiation damage. So with this, I'm going to move to the second part of the talk. What can we do with this motion-free cryo-EM data now? Of course, we saw radiation damage is still there, because all these linear plots continue to decay, and the rate of decay is the same. So how does this help to address anything about radiation damage, right? In essence, when we acquire a cryo-EM micrograph, this is what happens to our sample. And what we would like to be able to do is to rewind this movie and see what the specimen looked like before the onset of any radiation damage. This is not what we currently do in processing. Instead, in the processing, we would just take the average of all the frames of this movie and have our final semi-damaged structure. Now here, we're going to look at the movies of some density from a map of alpha ferritin calculated from a specimen support where there is movement and a specimen support where there isn't movement. And currently, both of these movies are stopped at the very first frame at 0.1 electron per angstrom square, and you can already appreciate that in this case there is hardly any density for anything, versus here the density seems fairly complete relative to the model. So first we're going to play the movie where the density is affected by the motion. So you can see we reach around 3 electron per angstrom square. The density is in agreement with the model and then deteriorates because radiation damage effects kick in, and by the end of the movie things like these carboxyls are completely gone, which is not surprising. And in comparison, the movie from the Hexafoil support, we start with the complete density, and then as we expose, the only thing that happens is the density deteriorates due to radiation damage. Another way to think about this is to plot the resolution of these individual frames as a function of fluence, which is shown below, and the black curve corresponds to the first movie, the red curve corresponds to the second movie. So in the case where there is specimen movement that the software could not correct, although it was attempted to, the resolution of the early frames is much worse. Then it kind of improves, and then it continues to deteriorate purely due to radiation damage. And we show that in the Hexafoil specimen support, the resolution is best in the beginning, and then it gradually deteriorates due to radiation damage, and that's it. The only thing that we're seeing in this movie is radiation damage. So now, with this knowledge, can we do something further with this movie? So what we would normally do with this kind of movies in the traditional processing right now is we would take the weighted average of all the frames. Meaning, if we reconstruct a map of our molecule at each frame, we could look at the structure factor or the Fourier component of this molecule at a particular voxel and watch how this structure factor decays as a function of fluence in the different frames, shown by these red squares. And then we calculate some approximate appropriate weights for our structure, which are derived from the data, and we calculate the weighted average of all of these red squares, which, as you can imagine, will happen to be somewhere here. So this will be our structure factor that we will put in our final map. However, if you imagine that this is a movie that shows radiation damage alone, and it shows this smooth progression of radiation damage, if you tried to fit a curve that describes this radiation damage decay, you could actually guess what the structure factor was at the very beginning, and it would not be this kind of weighted average somewhere in the middle of the data. It would be somewhere over here. So in essence, what all the traditional damage weighting algorithms do now is this over here, this red square, and we propose a new algorithm which, using motion-free data, can instead calculate this, the actual structure factors at zero fluence. This plot is just for the amplitude of a structure factor, and you could say we don't really worry about the amplitude because we're going to sharpen the map anyway, so we're going to adjust all the amplitudes. But the same phenomenon happens to the phase of the structure factor, and no amount of sharpening will fix that. So all the phases will be slightly skewed towards the somewhat damaged value. And this becomes more and more important the higher in the resolution you go. So here is the alternative approach. We watch the structure factor in a certain voxel change with fluence, and then we have a theoretical model. We fit this model to this decay, and we calculate the value of the structure factor at zero fluence by extrapolation. In a way, the structure factor is a complex number, so that's why we visualize this as these arrows in the real imaginary plane. This is the equation that we use to fit the progression of radiation damage. So we fit a B factor as a function of fluence, which increases linearly with fluence, which is quite well supported by the data at some constant rate, B dot, which we will be aiming to determine from the data. And then this affects the structure factor exponentially. The resolution comes here as k squared. And then there's two more complex numbers, the prefactor in front of the exponent, and some constant offset, which basically accounts for the fact that even if you damage your structure to infinity, it will not just disappear, it will become some Gaussian blob of material. So you have to use the experimental data at each voxel in Fourier space and determine these three parameters, two complex numbers and one real number. So in the end, just 5 numbers. And you go through all the voxels of your series of maps and do the same procedure over and over again. And in the end, you calculate the structure factor of at zero fluence using these fits, and you invert the Fourier transform to obtain the zero-dose extrapolated map. And this is meant to replace any damage weighting, which is what we're currently used to. So this is how this would fit into your standard cryo-EM data processing. You would still get your multi-frame movies, and you would drift correct them, meaning just whole frame alignment. And you will work with this drift corrected, potentially damage weighted micrograph to do all the usual stuff in whatever your favorite software is, like particle picking, 2D classification, 3D classification, refinements, etc., until you get your consensus map from your favorite particles and you have determined their 3D orientations and 2D offsets. After that, you use Reliant to use these particles and their already determined positions and angles to calculate a reconstruction from every frame of the original movie using the same particles. And you obtain some kind of series of reconstructions like this, where the earliest ones look best and the latest ones have no high resolution detail because they've lost it to radiation damage. After that, you feed this series of maps into our program called zero-dose. What that program will do is it will Fourier transform each of those, and then it will look at a specific voxel in Fourier space and will look how its value changes from frame to frame to frame. And for every voxel, it will fit this radiation damage model and calculate the intercept at zero fluence. Then it will populate the Fourier space with these intercepts and calculate the inverse transform to give you the map for the undamaged molecule. In addition, it will give you one more thing for free, which is a map of how fast does your molecule damage in every spot of the molecule. That is basically related to the rate of decay of this curve. And then you can take your zero-dose extrapolated map, open it in your favorite software, and color it by this damage rate, which we just define as the negative of the derivative of the structure factor with respect to fluence evaluated at the earliest fluence. And you can see all sorts of fascinating things, like how different side chains are differently radiation sensitive, and potentially this could be helpful for your model building, but also just for studying radiation damage in general. So in practice, just for those of you who will get the grid soon and try to do this on your favorite specimen soon, what you would have to do to get your zero-dose extrapolated map is, okay, you take your specimen, you plunge freeze it on the Hexafoil grid, you collect your movement-free cryo-EM data, which, as I explained, is very simple and just very similar to normal data collection. Then you process it as usual until you get your final 3D consensus high-resolution structure. Then you need to make sure that you have the following jobs done in Reliant: motion correction, particle polishing, and final 3D refinement. Then you can use this command from Reliant called Reliant Movie Reconstruct to get this series of maps for every frame of your movie. Then you feed this series of maps to our program called ZeroDose, and you just have to tell it some basic information like pixel size and per frame fluence. And the program returns two maps for you: the zero-dose extrapolated map and the damage rate map. And that's it. All right, with that, I just want to discuss a few limitations and requirements of this approach, which you should be aware of. So this definitely requires movement-free data. You cannot just take your old data set on carbon grids and try to do that, because the model that we try to fit is not valid in the presence of movement. And especially this is true because the amount of fluence, or how many electrons per angstrom square, destroy the information in your specimen as a function of resolution, scales with resolution squared. So let's say if we had frames affected by uncorrected specimen movement, this would be something like up to 3 electrons per angstrom squared, as we saw in the up-ferritin movies, meaning that the earliest sensible per frame resolution information you get is like past 2 angstroms. And after that, you need to sample this information reliably, at least for 3 frames, to be able to do this 5-parameter fitting. So actually, you don't have much signal left to do that. Instead, what you would need to do is you would need to have movement-free data. And if you're interested in this 2-point-something angstrom information, you would need to have at least 3 frames in your movie before you reach 3 electrons per angstrom squared. That means you have enough observations of the structure factors to be able to do this fitting. If your frames are more coarse, this will not work. And conversely, if your frames are less coarse, this will work better and allow you to do extrapolations even at higher resolution. And overall, here, what I mean by resolution is also the resolution of the individual frames. So this really requires the overall data set to be of really good quality for any of this to make any sense. All right, and I'm just going to finish with one example where we've used the Hexafoil support to determine this structure of this light harvesting complex from a purple bacterium. It's a very small membrane protein. Interestingly, we managed to visualize how does the bacterial chlorophyll, which is the reactive center in this molecule, get damaged by electron irradiation during its progression. And we've been able to extrapolate the map to the zero-dose fluence. However, this again highlights the limitation of the fluence fractionation of your data to begin with, because the dose in the first frame of our movie is already 1 electron per angstrom square, or in those units, something like 3 megagray. And from X-ray crystallography, we know that these metal centers are already damaged at 100 kilogray. So even in our first frame, this was not faithfully captured. This feature was already damaged, meaning that this extrapolation does not actually show us the undamaged state faithfully. And what would be required to actually get it would be to redo this whole thing at a much, much finer fluence fractionation, which luckily now is possible with the, for example, the new data formats like EER. All right, so this is just to summarize. So the zero-dose extrapolation is a new procedure which we intend to use as a replacement for damage weighting for movement-free data specifically. For now, this is a standalone program in C, but it easily integrates with Reliant and hopefully with CrySpark in the future as well. It returns for you the extrapolated map at zero dose instead of the damage-weighted map which you would currently have at the end of your processing. It is only possible in the absence of specimen movement, otherwise the radiation damage model just does not apply. It will only give you a significant improvement on your high resolution structure factors, because those are the ones that actually get damaged during your exposure. It definitely benefits from very fine fluence sampling, which is something to have in mind when you actually start collecting your movement-free data. And in contrast to damage weighting, this can account for local radiation damage rates, meaning that different parts of your structure could be radiation damage sensitive to a different extent, and this will be determined for you. And it will also give you this map of radiation damage rates. All right, so with that, I'm just going to wrap up with some kind of a wish list for the not so many remaining tasks to do in single particle cryo-EM data processing. So we're hoping to have this automated pixel size calibration soon using the gold reflections, so there is no more confusion about what my pixel size is. Would be neat to have on-the-fly whole area drift correction just for the preliminary movie alignment. We still think the CTF correction, the way that it's done normally, could be improved, and we're very keen on evolved sphere-aware refinements and single sideband CTF correction and pre-multiplication, which would allow you to extract your particles in small boxes, which is great for computational purposes. There are some things in CTF refinement with which we don't really agree, like why can we not have all the physical parameters that we actually know for sure, have them fixed and only refine the unknowns. Kind of related to this, if we want to group our data into beam image shift groups, it would be nice to have some restraints on the CTF parameters, and would be nice to know the errors in these estimates. And finally, I showed you Reliant already has some features to do these per frame reconstructions. It would be nice if this was a bit more streamlined. And we're hoping to incorporate this zero-dose extrapolation and radiation damage sensitivity mapping into the software for easier use. Right. With that, I'd like to thank my group. So my supervisor, Chris, who we already saw the talk from. Jude worked a lot on the zero-dose implementation. Pepe worked with us in the beginning of the fabrication of the small hole gold grids. And Joshua has been very helpful on all topics regarding radiation damage. And Matthew has been a great support in the experiments in the lab. Thank you for your attention.